Hi there. This is John Buys, and this is Edinburgh Explorations put on by the University of Edinburgh. And this is the first part of a series I'd like to do where I explain the standard model of particle physics, which is our currently most favored theory of the fundamental particles that make up the whole universe. You've probably heard about some of these particles, and this picture here shows all of them in the standard model. We've got 6 leptons. We've got 6 quarks. We've got various gauge bosons, which carry the forces. So the gluons, of which there are 8, carry the strong force. The photon carries the electromagnetic force. The weak bosons, of which there are 3, carry the weak force. And then, in addition to all of those, there's this famous particle you must have heard of called the Higgs boson, which is not a gauge boson. It's not really a force-carrying particle. It endows the other particles with their mass. And these blue curves here show which particles interact with which other particles. So this is a quick overview picture of the standard model, which is actually a mathematical theory and which I'd like to explain. And it'll take quite a while to explain all the math of the standard model. I probably won't even explain all of it, just a chunk of it. But today I'd like to get started by getting you to know the standard model a little bit, and a little bit of history might help there. So back in the 1800s, people started messing around with tubes like this, where you took a tube of glass, you evacuated it, and you ran a current between two little metal spikes. And some of them are called cathode ray tubes, and some of them are called anode ray tubes. But either way, it turns out that you get a glow in your evacuated tube. There's a little bit of gas in the tube, and it glows. And people studied it, and they realized eventually that this glow was because those metal spikes, called the cathode and the anode, actually shoot out particles. And that's where we started seeing elementary particles. So let me tell you about them. That's where particle physics began. And I'll tell you about how it began and how it went on. So in 1897, a fellow named J.J. Thomson discovered the electron. He discovered that cathode rays produced by the cathode in one of these tubes were actually lots of little particles of a very small mass, and he was able to figure out the ratio of the charge to mass of these particles, and they got called electrons because they were clearly connected to electricity, which was already studied quite a lot. The symbol for an electron that we use now is E minus. The minus is because the charge of the electron is negative by convention. We just picked convention so that electrons come out to have negative charge. And we say that it has charge -1 because it's sort of fundamental in that way, although we'll see some twists in the story later on. And it has a very small mass, but I'm going to tell you its mass in units of electron masses. So it has a mass equal to 1 electron mass, and that's a nice unit to compare other particles to. Now, in 1898, a year later, Wilhelm Wien discovered that anode rays coming from the other end, the anode, were also due to particles, and they were actually hydrogen atoms that had their electrons stripped off of them, so they're called hydrogen ions. But by now we realize that they are actually a fundamental particle, well, a pretty fundamental particle in its own right, called a proton. I was laughing about that because later we'll see that protons are made of even smaller parts. But at the time, proton counted as a fundamental particle. It's positively charged, charge +1, and it's much heavier than the electron. Its mass is about 1,836 times that of the electron. And just for fun, I'll say that it's 0.15, just so you know that it's not an integer, times the mass of the electron. It's some crazy number, and nobody knows why it is this number in a fundamental sense. It's still a deep mystery why particles have the masses that they do. Now, in 1905, Albert Einstein hypothesized that light came in discrete units called by him quanta. Later on, people began to realize that these quanta were actually particles, and they got the name photons. And we have a symbol for them, gamma, because very energetic photons are called gamma rays. They were called gamma rays back in those old days and still are. So that's our name for the photon, gamma. They have no charge. And Einstein realized that later that something that has no mass can only move at the speed of light, and that photons, because they move at the speed of light, conversely, must have no mass. So they have zero mass. Now, it took people a long time to understand photons or believe in photons. So Einstein didn't start out calling them photons. He called them quanta, somewhat mystical entities. That name gave rise to the name quantum mechanics. And there had been a long dispute before Einstein about whether light was particles or waves. And the wave theory had been triumphant until this issue came along. Planck realized that something funny was going on with the amount of light coming out in different frequencies out of a hot oven, what we call black body radiation. And he realized that you could only get the experimentally observed answer if energy came in little quanta. But he didn't really understand what he was doing, actually. He didn't really know that he'd invented quanta. And so it wasn't until 1905 that Einstein clarified that. And it wasn't until later that Einstein and others started inventing quantum mechanics to explain this, and also to realize that photons must have momentum as well as energy. And so it was by 1922, quite a bit later, that Compton was able to measure the momentum of photons, that is, to actually do experiments where you can feel photons hitting things. And then it became clear by that point to everybody that photons were really particles. This is really tied in with the whole history of quantum mechanics, and it's a wonderful story of which I'm just telling a tiny bit because we have to move on. We're trying to get to all the particles here in the Standard Model. And so in 1920, Rutherford postulated the neutron. So what happened was that these anode rays, of which the proton is one, actually come in many kinds, and we now say it's because different kinds of atoms can have the electrons stripped off of them, and their nuclei will be made of different numbers of protons and neutrons, so they will have different charges and different masses. But back then, this was all much less clear, and people just noticed that there were different kinds of anode rays, and they discovered, for example, that when you ionized helium, there was this anode ray that had about 4 times the mass of a proton, but only twice the charge. And eventually people realized that that was because a helium nucleus is made of 2 protons, but also 2 neutrons. So it was a kind of detective work required to discover that there must be these neutrons at the center of the atom. And it wasn't only until quite later, namely 1932, that Chadwick was able to make beams of neutrons by themselves and study them as particles on their own. As we'll see, a neutron by itself doesn't last forever, so you don't just find them sitting around in nature. A neutron, as the name suggests, is electrically neutral, so it has charge 0. And as I said, it has mass pretty close to that of the proton, but suspiciously slightly different, 1,838 point something, 0.68 approximately, times the mass of the electron. So this was very fascinating that there are these two particles, the proton and the neutron, that are very similar in some respects. They both stick together to form a nucleus, but they're not the same. They have completely different charges and slightly different masses. How does the nucleus stick together? The protons repel each other because like charges repel. The neutrons are neutral, so they don't help things stick together using electromagnetic force. Some other force must be holding together the nucleus. That later got called the strong force, and we will get to it. So that's a mystery at this point in the story. Now, in 1932, another big discovery occurred, which was the discovery of antimatter. Dirac's theory of the electron actually predicted that there should be an anti-electron, a particle with the same mass as the electron, but the opposite charge. And we now call that the positron. And because it's positively charged, and we call it E plus for an abbreviation. But it was in 1932 that this was actually discovered. In fact, people had already seen it, but they just didn't believe it because they didn't expect it. But once they looked for it, they quickly found it. And it turns out that not just electrons, but all particles have their own antiparticles. So there's an antiproton, which, well, we might call it P minus, but for some reason people call it P bar, where the bar symbol stands for antiparticle. And there's an antineutron, and so on. So at this current stage of the story here, the things to look for would have been the antineutron and the antiproton. Since they're a lot heavier than the positron, it took a lot more work to get a hold of them. I believe they first found them in cosmic rays, that is, shooting down from the sky, naturally produced. Later on, people figured out how to make them. And what about the photon? Well, interestingly, the photon is its own antiparticle. So that's a possibility too. And it's possible for the photon, of course, because it has charge 0, so its antiparticle would also have charge 0, and it turns out that it's itself. The neutron also has charge 0, but it's not its own antiparticle. So it's not just electric charge that's involved in distinguishing a particle from its antiparticle. And we'll learn more about that as we go on in this story. So people began developing what's called quantum electrodynamics, which is a theory of how photons interact with other particles. They interact with charged particles. And the simplest version of this story is that if you have an electron moving along, which I'll draw this way. So think of time as going up in this picture. And you have an electron going along. It can actually emit a photon, which is this wiggly thing, and it remains as an electron. And this is the basic process whereby electrons or other charged particles interact with photons. This little event here of emission is called a vertex. And the neat thing about this kind of picture, which was invented by Feynman and called a Feynman diagram, is that you can fiddle around with it in various ways and get other legitimate pictures. For example, if we did it this way, so again, we're reading time as going up the page. Here we have an electron moving along and absorbing a photon. So that's another thing that can happen in quantum mechanics of the interaction of photons and charged particles. But you can also have other things. For example, you can have positrons and electrons do various interesting things. For example, we can take this picture here, we can rotate it a bit. And now notice one of these arrows could be pointing up and the other one pointing back down. And the photon comes up here now. What's this? Well, this is still an electron, and this is still the photon. But what's this arrow going back down? Well, that turns out to be a good way to think about a positron, the antiparticle of the electron. I will call it, I'll label it with a positron here, E plus. So what is this thing? As time is going up the page, we see an electron and a positron colliding with each other and turning into a photon. So that's a possible thing, although those of you who know a lot of particle physics know that this process can't happen all by itself. It must actually be accompanied by the emission of another photon. Nonetheless, this is one step in that larger process. And so the point is that these Feynman diagrams are a way to think about interactions of particles, and you can rotate them and think about different things in terms of the same basic vertex. So I encourage you to rotate this picture even more and see what else you can come up with using this scheme here. So now, why am I telling you all this? Well, this is, of course, the kind of stuff we get into when we get into the standard model. But the reason why I'm telling you about it right now is because I mentioned that the neutron is not stable. The neutron doesn't last forever. So the neutron, in fact, what does it do? If you have a neutron just sitting there, after a while, randomly, in a kind of radioactive half-life kind of way, just sort of randomly at some moment, will turn into a proton and an electron. That was very interesting to people, and they studied it very carefully. This sort of shows that neutrons and protons are related because one can turn into the other, but somehow the electron gets into the game here too. And they discovered that energy was not conserved, or seemingly not conserved in this process. The output had less energy than the input. That made Pauli hypothesize that there was some other particle coming out of this reaction that carried away the extra energy. This other mysterious particle, since we didn't actually see it, would have to have charge 0 and have to be fairly light, because if it was very massive, its mere mass would make it have a lot of energy, and there was only a slight bookkeeping error in the energy conservation here. So after some thinking about all this stuff, people decided that what this mysterious particle was, well, we now call it an electron antineutrino. So nu E is our name for the electron neutrino, and it's a very light, chargeless particle that has electronness in it in some sense. This antineutrino, the electron antineutrino, has, you might call it anti-electronness. What the hell do I mean by that? Well, the idea is that there's no electron at the start of this reaction. There's an electron at the end. So there seems to be an electron coming out of thin air, but electronness is conserved because this antineutrino has anti-electronness. So this does bookkeeping, keeps the books balanced in several ways. It not only leads to conservation of energy, but it leads to conservation of electronness or electron number. So Pauli theorized this in 1930, and people were very suspicious of it because making up new particles just to balance the books is a slightly fishy endeavor. But later on, people were able to detect neutrinos and antineutrinos by letting beams of them hit other chunks of matter and causing other reactions, like the reverse of this reaction, for example. And so by 1956, the theory of neutrinos was confirmed. So that's the story up to a certain stage. Let's summarize where we are right now in terms of particles and introduce some terminology. So there are these big, heavy particles. I mean, they're not physically large, they're just massive, is what I mean, called hadrons. And those are the proton and the neutron. And then there are these lighter particles called leptons, from a Greek word meaning something like weak or wimpy. And those are the electron, neutrino, and the electron. And all of these have antiparticles, so I won't draw those. So you'll notice something interesting here, that they come in pairs, right? There are two hadrons and two leptons. It turns out that in the standard model, we see similar things going on. So this was not a coincidence, as it turns out, ultimately. However, we now know that this process of a neutron turning into a proton is actually something else. If we look at it very carefully, we have by now discovered that a proton is not a fundamental particle. It's actually made of other particles called quarks, and it's made of two up quarks and a down quark. So we're getting into the theory of quarks now, and I'm not telling you the whole history of how this evolved, because in fact, the proton and neutron are just among many hadrons that people later discovered. So the story became extremely complicated for a while and was dramatically by the discovery of quarks. So in 1964, Gell-Mann theorized that hadrons were made of quarks, and the proton made of two ups and a down, and the neutron made of one up and two downs. So without going into much detail about that, I just wanted to mention that the decay of the neutron into the proton that we saw before, remember, a neutron can turn into a proton, an electron, and an antineutrino. That's actually what's really going on there, is simply that one down quark in the neutron is turning into an up quark, which makes it be a proton. So what's really going on is more like a down quark turns into an up quark and an electron and an antineutrino. This is closer to our modern way of thinking about it. However, we know that this second process here is actually not really what's going on quite either. It's part of the story, but let me draw the whole story. Let's draw it as a Feynman diagram, then you'll see what's going on here. So we have this down quark coming in, it turns into an up quark, but it does not instantly emit an electron and an antineutrino at the moment that that happens. What in fact happens is that it emits a different particle called a W boson, called a W minus, in fact. It has charge -1. And that then turns into the electron and the antineutrino. And I'll draw the antineutrino as a downwards pointing arrow because it's an anti-particle. So what's going on here is not actually a single process, but two processes. One where an up and down interact with a W boson, and another where the W boson interacts with an antineutrino and an electron. So Feynman diagrams are the way to really understand what kinds of processes can occur that turn fundamental particles into other particles. And we're seeing here that this interaction is somehow similar, but also in many ways different from the one I mentioned before, where an electron can interact with a photon. What's common, we'll see, is that we have quarks or leptons interacting with gauge bosons, these wiggly guys, but they are different in various other ways. For example, the electron doesn't turn into something else, whereas here the down quark is turning into an up quark. This process of something turning into something else, like a quark turning into another quark, is connected to what's called the weak nuclear force. It's weak, and that's why it takes so long for a neutron to turn into a proton. So let me try to give you like an updated version of the little chart I had here that takes more of this modern knowledge into account. So we have quarks and we have leptons. So instead of hadrons and leptons as before, we have quarks and leptons in the more modern understanding. We have this up quark and this down quark. We have this electron neutrino and the electron. But as people continue doing particle experiments, they discovered various other particles, which is why I'm leaving a lot of room in these charts. First, they discovered that in addition to the electron, there's another particle very similar to the electron, but 207 times heavier, called the muon. And then they discovered that that also has its own kind of neutrino. They discovered that there were more than two kinds of quarks. There's a so-called charmed quark and a so-called strange quark that are very similar to the up and the down. As you can see, the names are starting to get a little bit silly. That's because people were discovering all these particles faster than they could mentally process them, and it started seeming a little silly. And finally, they found a bottom quark and then a top quark, and also another pair of leptons, so-called tau lepton, which you might call a tauon, but people call it a tau lepton, and also a tau neutrino. So this is all, as far as we can tell. We've got pretty darn good evidence that there are no more leptons or no more quarks unless they're like extremely heavy and not much like the ones we've seen so far. Now, there's something pretty wild about all this. If you do the bookkeeping on electric charge, you can figure out what charges the quarks have got to have. So a proton had charge 1, and it was 2 ups and a down. The neutron had charge 0, and it was 2 downs and an up. So what could the charges of the quarks be to make the charges balance or equal each other? Well, you could do the math. You could pause this video and figure it out for yourself, but it's easy to see when someone tells you that it works when the up quarks have charge 2/3, and the down quark has charge minus 1/3. And that is the only possibility for how it could work. You can do the algebra and solve for these charges. So here we get 4/3 minus 1/3 is 1. Here we get 2/3 minus 1/3 is 0. So these quarks are pretty far out. They have charge that is not an integer times that of the electron. They have charges 2/3 and -1/3. Everybody who first hears about quarks finds this unbelievable or strange, but we've done experiments that prove that that's true. So they're different than the leptons, which have charges 0 and -1. But you'll notice the difference of these two numbers is 1, and the difference of these two numbers is 1. And believe it or not, that seems to not be a coincidence. There's that similarity between the quarks and the leptons. When we get to grand unified theories, if I get around to it, we will see some possible theories that explain these crazy numbers. But now let me just round out the list of particles in the standard model for you. So I started telling you about these gauge bosons. Those are the particles that carry forces. So the idea is that quarks and leptons form matter, whereas the gauge bosons are particles that carry forces. And the first force I started talking about is electromagnetism, the electromagnetic force, like how charged particles repel each other due to the that's due to the electromagnetic force. The electromagnetic force is carried by this gauge boson called the photon, as I mentioned. But there's this other force called the weak force that's key for particles transmuting into other particles. And there are 3 gauge bosons that carry the weak force, called the W plus, because it's positively charged, the W minus, and the Z, which is neutral. I guess these are just called weak bosons collectively. And then, what I haven't gotten to at all yet is what holds the nuclei together. I mentioned that there has to be some force holding them together because the protons repel each other. Or for that matter, what holds the quarks together. That turns out to be a third force, and it has to be very strong to do its job. So people uncreatively call it the strong force, and they uncreatively call the particles for it gluons, because they stick things together. And there are actually 8 of them. They don't have very exciting separate names. So I'll just say there are 8 of those gluons there. We understand quite well why there are 8. We understand quite well why there are 3 of these weak bosons and why there's 1 photon. One thing we don't understand at all is why these quarks come in 3 bunches and why the leptons come in 3 bunches. Those bunches are called generations. So we say that there are 3 generations of quarks and of leptons. And we do, in our theory, have some reason for believing that there should be the same number of quark generations as lepton generations. Our theories wouldn't work if that were false. But it's just an empirical fact, as far as we know so far, that there are 3 generations and not 1 or 4 or something else like that. So that's still quite mysterious. So I've introduced all the actors in the drama of the standard model. So let me just go back to this chart. So this chart shows all those actors, and these blue curves here show how they interact with each other. So for example, the quarks feel the strong force, so they interact with the gluons. They are charged, so they interact with the photon. They interact with the weak bosons, and that's what accomplishes one kind of quark turning into another. The leptons do not feel the strong force, so they don't interact with the gluons. The leptons do turn into each other using the weak force. So we do have this blue arc here. And the electron, muon, and tau are electrically charged, so they interact with the photon. The quarks being charged interact with the photon as well, but the neutrinos are uncharged and thus don't interact with the photon, which is why you don't have a blue line going up there. Now, the gauge bosons, in some cases, they interact with themselves. The photon is uncharged and thus does not interact with itself. But the gluons do carry the kind of charge that is relevant to the strong force, so they do interact with themselves as well as interacting with the quarks. We say they are non-abelian gauge theory, and we will sometime talk a bit about what that means. Similarly, the weak bosons interact with themselves. And finally, the Higgs boson interacts with everything that has mass and gives it its mass in a mechanism called the Higgs mechanism, which I will sometime endeavor to explain, I hope, if I go on long enough. So it interacts for sure with the charged leptons and with all of the quarks and with the weak bosons, which do have mass. It interacts with itself because it itself has mass. It does not interact with the photons and gluons, photon and gluons, because they don't have mass. And finally, we are still a little bit mystified about the neutrinos. They do have mass, but we're less sure that that mass is due to the Higgs boson. So the person who drew this chart cautiously drew the Higgs boson blue line just going to these three leptons and not to these neutrinos. Personally, I bet the Higgs boson does interact with the neutrinos as well, but that hasn't been definitively proved yet. So that's all the interactions between all the particles in the Standard Model. For each one of those kinds of interactions, you can draw a Feynman diagram vertex. Then the math comes in. How do you actually do any calculations with the Standard Model to predict how rapidly particles turn into other particles, or at what rate that happens, et cetera, et cetera, et cetera? That's where the math comes in. That's called quantum field theory, and I'm not sure how much I'll get into that in my course on the Standard Model. What I definitely want to talk about is the symmetry group of the Standard Model, which is called SU3 times SU2 times U1. Those three crazy things, SU2 and SU3 and U1, are Lie groups, which are the symmetry groups responsible for we need to understand the three forces. And we'll have to get into some Lie group theory and some representation theory to make that all precise. So I wrote a paper a while back with John Huerta about the math of this stuff, and I'll link to it below the video. And I plan in my course to go through that paper, which is an expository paper, and tell you about how the Standard Model works in a bit more detail, without it being a full-fledged course on quantum field theory. So you will not be able to leave this little mini course being able to do a lot of calculations about how particle physics actually works. That would be a serious course, but this is just a fun course. And so what you will simply know is more of the math behind the symmetry of the Standard Model. And maybe if we get far enough, the symmetries in these grand unified theories, which people have introduced to make sense of this. As you can see, this is a quite messy, complicated, mysterious bunch of stuff. And so it's really remarkable that some grand unified theories called the SU5 and spin 10 grand unified theory put a whole bunch of this into a much neater package and reveal that it's not as wacky as it looks. For example, there's a reason why the quarks have charges 2/3 and -1/3 in those grand unified theories. And so that's very satisfying. So I hope that you stick with me to the point where I get to talk about that stuff. But we'll start out introducing some of the math of the Standard Model. Okay, so I hope to see you in further videos about the Standard Model, and I hope you have lots of questions and ask the questions below, and I'll do my best to answer them and we can talk about them.